This is your Benchmark 1 review. You can follow along using your review packet, and you can access more reviews and notes at srhschem.wikispaces.com. The first section that we're going to work on is atomic structure. First question asks us to complete a table. We have to fill in the charge and location of the subatomic particles. Protons are positive, neutrons are neutral, and electrons are negative. Both protons and neutrons are located in the nucleus, whereas electrons orbit the nucleus. Number 2. What two subatomic particles add up to make the mass number of an atom? So this is a question about where most of the mass of an atom comes from. So up here I've got protons and neutrons, and here are electrons. If you compare the two, you see that protons and neutrons are much larger than electrons. Protons and neutrons are like bowling balls, whereas electrons are like marbles. If I have 15 bowling balls and I see how much that weighs, and if I add a few marbles, it's not going to make much of a difference in the total weight. So most of the mass in an atom comes from protons and neutrons. So if I take the sum of the number of protons and the number of neutrons, I will get the mass number. What is the difference between mass number and atomic number? How can you use these to find the number of neutrons in an atom? Well, first, the mass number, again, this is from last slide, most of the mass comes from protons and neutrons, so the mass number is the sum of protons plus neutrons. The atomic number is equal to the number of protons, and one way you can remember that is with AP. A stands for atomic number, and P stands for number of protons. If I were to take the mass number and subtract from the atomic number, I could write it out like this. Protons plus neutrons, that's the mass number, minus the atomic number, which is the number of protons. So whenever I carry out my algebra here, I'll cancel out protons, and it leaves me with only neutrons. So by subtracting the mass number from the atomic number, we can find the number of neutrons. Question 4 has another table. In this question, all of the elements are neutral. So we're going to start with sodium. I need to know the number of protons and the number of electrons. Now if you look on the periodic table, you can see that sodium is atomic number 11. And remember, atomic number is equal to the number of protons, AP. So it's atomic number 11, which means that we have 11 protons. Now because this particular atom is neutral, I'm going to have the same number of protons as electrons. So each proton is plus 1, and each electron is minus 1. So I have to have an equal amount of each for the charges to cancel out to 0. In the next one, we're not given the element. Instead, we just have the number of protons. Well, again, the number of protons is equal to the atomic number. So if we look on our periodic table and we look for atomic number 16, we see that it's sulfur, or S. Now because this is neutral, I'm going to have just as many protons as electrons. So I have 16 protons, which means that I have 16 electrons. And the last one only gives us the number of electrons, but we know since this is neutral that there are just as many protons as electrons. So there are 3. And then if we look on our table of elements, we see that atomic number 3, which is the number of protons, is lithium, or Li. Question 5 asks us to determine how many electrons are present in a neutral atom with atomic number 32 and mass number 73. So this question has a red herring in it. It's got one number in there that's set to confuse you. The mass number of 73 isn't going to be important to us unless we're trying to find the number of neutrons. in this particular problem, we're solving for the number of electrons. So the atomic number is 32. And in a neutral atom, the atomic number is equal to the number of protons, which will also be equal to the number of electrons. So because my atomic number is 32, that means I have 32 protons, so I have to have the same number of electrons, 32. Again, atomic number equals number of protons, so we can solve this. Protons is equal to electrons because we have a neutral atom. So number 6 is a complete the sentence problem. Isotopes are atoms of the same element with the same number of protons, but a different number of neutrons. So anytime that I have the same number of protons, that's the same atomic number, it means it's the same element. But where isotopes vary is in their number of neutrons. So, number 7, we have isotopes notation here, and it asks us to explain why the following examples are or are not isotopes. So let me remind you what the numbers mean. The bottom number is the atomic number, which is equal to the number of protons. So that should be the same for all isotopes because they're atoms of the same element. They have the same atomic number. The top number is the mass number. Now remember, most of the mass in an atom comes from protons and neutrons. So the mass number is the sum of protons plus neutrons. So let's go ahead and look at the first example. This one we know isn't an isotope because here we have hydrogen and here we have helium. These are different atoms, so they can never be isotopes. So those guys are not isotopes. In this second example, we see that we have both hydrogen, so that's good. But take a look at this bottom number. The atomic number of hydrogen is 1. So both of these should have 1 on bottom. They should have the same atomic number. But because this has a different atomic number, it means that these guys aren't isotopes. This is written wrong. This should be a 1 instead of a 2. The last example, everything is right in this one. They're both hydrogen. The atomic number, which is on bottom, is 1 for both. So that means they are, in fact, the same element. And the top number is different. So this means that this has 1 proton. This means that I have 1 proton plus 1 neutron. So they have the same number of protons, but they vary in their number of neutrons. So this is the correct answer. Number 8 is another complete the sentence. The development of the modern atomic model is based on the work of many scientists over a long period of time. Whenever we learned about all of the different models of the atom, we started with Democritus, and Democritus was active in 400 BC. We then worked all the way up to the quantum mechanical model, which is in use today. So that's more than 2,000 years, and many scientists worked on this over that time. In number 9, I want you to describe what happens to electrons in atoms as they gain and lose energy to move between energy levels. We saw this whenever we did our flame test lab. So here I have an atom. I have a Bohr model of the atom. And the energy levels are represented by these rings. The nucleus is right here in the middle. So these rings represent energy levels of the electrons. So if I have an electron and it's sitting in this first energy level, it can gain energy. One of the ways it can gain energy is by burning it by passing it through a flame. So whenever it gains energy, it's going to jump up in energy levels. Now simultaneously at the same time, electrons that are excited and are in this energy level can drop down by losing energy. And the way they lose this energy is they emit it as light. And the color of the light depends on exactly how far down it fell. So the greater the distance the electrons travel, the more energy is released. The different colors of light result from that different amount of energy. So whenever they gain electrons, they go up in energy level. Whenever they lose energy, they go down in energy level and emit that energy as light. So we've now reached part 2, which are questions that focus on the periodic table. Our first question asks us to give an example of an alkali metal, a noble gas, and a metalloid. So if you look on your table of elements, the alkali metals are going to be found in this first column, except hydrogen. So a possible example of alkali metal could be lithium, sodium, potassium, or any of the other elements that are in that first column. Noble gases are found at the opposite end. Noble gases are in the last column here. So anything found in that last column is a noble gas. So that could be helium, neon, argon, or any other element that's found in this last column. Now metalloids, shown in green here, could be anything like silicone, boron, germanium, arsenic. These are all examples of metalloids. Now, on your benchmark, you're going to have a provided table of elements. It will have a staircase going down like this. So, pretty much anything except for these two things at the end here that touches that staircase is going to be a metalloid. So again, that could be something like silicon, germanium, arsenic, anything that touches that staircase. Question 2 asks you to consider the information below to figure out which group, those are the columns, the element would belong to. So if we look at the first set of options here, we have malleable and conducts electricity. That sounds like a metal to me. So if I look at my periodic table of elements, if I look at column 18 all the way at the end, that's going to be noble gases. Now, those aren't malleable because they aren't solid. The next option is column 15, which has nitrogen, phosphorus, arsenic, antimony. A lot of these are metalloids, and that's because they touch that staircase. Nitrogen is a gas, so it's probably not going to be 15, so that's probably not going to be our best choice. The only element in that column that behaves remotely like a metal is bismuth all the way at the bottom. So that leaves only one choice, and that's group 1. Group 1 has got lithium, sodium, potassium, rubidium, and these are all metals. So the one that is malleable and conducts electricity, this best applies to group 1. We're going to apply the same process to the next one, which tells us that the characteristics are brittle and they lack luster. So we just decided that the first column was metals, so it's probably not going to be 1. The second column, 2, is pretty close to the first column. And again, magnesium, calcium, strontium, these are all metals as well. Metals are malleable and they are shiny, which is the opposite of brittle and lacking luster. So by process of elimination, that leaves us with 16. But again, in column 16, I've got selenium, I've got sulfur. That was what we crushed in our lab, the yellow substance that we hit with the hammer and it broke apart. The last question asks us which group is all gases. So again, we already decided that group 2 was metals, so probably not going to be that one. If we go and look at group 6, that's chromium, molybdenum, tungsten. These are all metals as well. But the last column, column 18, that's the noble gases. So in this case, the answer is going to be 18. These numbers, you can find them if you look on your table. They're actually written out there for you, so there's no need to count or to guess. It says right at the top, group 1, 2, 3, all the way over to 18. So number 3 is a very important question because it's asking us to summarize all of the periodic trends. As we go down a group, which means from top to bottom, and as we go across a period, which means from left to right. So the first trend we're going to start with is atomic radius. Atomic radius is the distance from the center of the nucleus to the edge of the electron cloud. So as we go down a group, this way, we are increasing the layers of electrons. The more layers of electrons there are, the less attraction there's going to be between the nucleus and the electrons, which means that as we go down a group, the atomic radius is going to get larger. Because there's less attraction, there's less to hold those electrons close to the nucleus, so we get a bigger atomic radius. Whenever we go across a period, it's the opposite trend. We have an increase in atomic number as we go across the period, so as we go this way, atomic number goes up, and atomic number is the number of protons. So the more protons I have, the more positive the nucleus is. So then the attraction between the nucleus and the electrons will be stronger. So as I go across a period, the atomic radius is going to get smaller. It's going to decrease. And that's because there's more attraction and the electrons are held more closely to the nucleus. The next trend we're going to talk about is ionic radius, and that's just the radius of an ion, which is a charged particle. So there's two types. There's cations, which are positive, and there's anions, which are negative. Now, whenever we form a cation, we're taking away an electron. Electrons are negative, so if I take away a negative charge, I'm going to be left with positive charge. So whenever an element loses an electron, the attraction between the remaining electrons and the nucleus becomes stronger. So the ionic radius becomes smaller. So that means that as we go down a group and we lose an electron, the size of the ionic radius is going to decrease. Now, as we go across a period, depending on whether or not we have a cation or an anion, we're going to have a decrease in size. The next trend that we're going to talk about is electronegativity. And that is the ability of an atom to attract electron. So the more electronegative an atom is, the more it wants electrons, the more it attracts them. As we go down a group, we're going to see a decrease. As we go across a period from left to right, we're going to see an increase. Now, the reason behind this has to do with an octet. Now, most elements, whenever they're stable, whenever they have 8 electrons in their outermost s and p orbitals, they're going to be the happiest. They're going to be the most stable. So if you look here, the elements in this column, if we did the electron configuration of them, we would have S2 and P5, and they would all be different energy levels, but overall we would see 2 electrons in the s orbital and 5 in the p orbital. So this means all the elements in this column have a total of 7 electrons. So if they got one more electron, they would be stable and they would be happiest. So the elements that are in that column really, really, really want to get an electron. Whereas elements that are over here, these guys are going to have a configuration of S1. Now, if they lost that one electron, they would go down to the previous energy level, which would be a lower energy level, but it would have 2 electrons in the s orbital and 6 in the p orbital for a total of 8. So if the elements in this column lost an electron, they would have a full octet. So those elements really, really want to lose an electron. Ionization energy is the energy required to make an ion, and this is achieved by removing an electron. So the more tightly the nucleus is holding on to those electrons, the harder it's going to be for me to rip off one of the electrons to form an ion. So that means that as we go from top to bottom, the ionization energy is going to decrease. So as I go down the column, the electrons aren't held as tightly to the nucleus. This means it's easier for me to pull one off. We see the opposite whenever we go across a period. Whenever we go across a period, I get more protons. I get more positive charge holding on to my electrons. So those electrons are held on more tightly to the nucleus. So as I go across a period from left to right, I get more protons. It gets harder to pull off an electron, so the ionization energy increases. The last trend is metallic character, and this is how much a particular element acts like a metal. So in this case, the most metallic element is going to be francium down here. So the closer something is to francium, the more it acts like a metal. So as we go from top to bottom, the metallic character is going to increase. And as we go across a period, that's from left to right, so as we move away from francium, the metallic character decreases. So the next question is asking which of the options best describes metalloids. So if we look at the first option, malleable and ductile, well, that describes metals. So that's not going to work. Only describes metals. Good conductor of heat. Well, that's also metals. Metals are excellent conductors of electricity and heat. So the first two options describe metals. Now, if we look at the last option, it has properties of both metals and nonmetals. And that's exactly what a metalloid is. It's something that's got properties of both. It's sort of in between. So the correct answer for this one is going to be the bottom, properties of both metals and nonmetals. Number 5 asks us which of the following pairs would have the most similar chemical properties. So if we look at our table of elements and we find, let's start at the bottom, if we find phosphorus and chlorine, that's going to be over there in the P block, atomic numbers 15 and 17. So if you look at that, those guys are separated by an element, so they're not particularly close to each other. So we're going to go ahead and eliminate that option. We're looking for which elements are closest together. If we look at potassium and bromine, that's atomic numbers 19 and 35, they're at complete opposite ends of the table. So it's not going to be these guys. So then that leaves us with lithium and beryllium and magnesium and calcium. Lithium and beryllium are right next to each other on the periodic table, atomic numbers 3 and 4. Magnesium and calcium are atomic numbers 12 and 20, and they are on top of one another. Now in the modern periodic table, the elements are grouped based on similar properties. So the groups are the columns. So lithium and beryllium are in different columns, so they're going to have less in common than magnesium and calcium, which are in the same column. So we can eliminate lithium and beryllium, and that leaves us with magnesium and calcium. The reason your choice in number 5 is correct, again, it's got to do with the fact that we're looking for the two elements which are closest together. And in addition, they need to be in the same column. So the elements selected for number 5 are the two that are closest to each other on the periodic table and therefore the most similar. And I would add to this that they're also in the same column, so they have more similar chemical properties than lithium and beryllium, which are next to each other. So number 7 is asking us to arrange the following in order of atomic radius from smallest to largest. So if we look at our periodic table and we look at our trends, atomic radius is again the size of the atom from the center to the edge of the electron cloud. So in this case, the smallest one is going to be fluorine. So fluorine is the smallest one, and all of these other ones, we're going to rate them based on how close they are to fluorine. So if we take a look, we can find francium, okay, that's in the opposite corner, atomic number 87. Nickel is atomic number 28. Iron is atomic number 26. Cesium is atomic number 55. So go ahead and locate those on the periodic table, and we're going to look for the one that is closest to fluorine. And in that case, it's going to be nickel. So nickel is the next closest. After that, the next closest one is iron. Then if we look, we just got to compare cesium and francium. So cesium is a little bit closer, so that's going to be 4. And francium is the furthest away, so that is 5. Which of the following has strongest metallic character? So you have to locate these 4 elements. You have tin, lead, antimony, and bismuth. And if you find those guys kind of form 4 corners, atomic numbers 50, 51, 82, and 83. So again, the most metallic element is going to be francium. So the closer something is to Fr, the more metallic it is considered. So if you look here, the closest one is going to be the one in this bottom left corner, and that is lead, Pb. Question 9 is asking us about the relationship between ionization energy and atomic radius. So, ionization energy is the amount of energy that I need to pull off an electron. Now, the bigger the atomic radius is, the further from the nucleus the electrons are. So if this is my nucleus, okay, I'm going to do 2 nucleuses here. If my electrons are really far, the red dots are really far from the nucleus, then it's going to be easy to pull one off. Whereas if they're really close, the attraction between the electrons in the nucleus is strong. So it's easier to pull an electron off of this atom than it is to pull one off of this atom. So as the atomic radius increases, the electrons are further away from the nucleus, which means there's less attraction, and it's going to be easier to pull off an electron. So ionization energy decreases as atomic radius increases because the electrons are further from the nucleus and there's less attraction, so it's easier to pull off an electron. So again, larger atomic radius means that the electrons are further away from the nucleus. Further away means it's easier to pluck off that electron. The easier it is to remove an electron, the lower the ionization energy. So we're going to go ahead and take a look at part 3, which is about numbers. First question is a conversion. It's asking us to convert 1,895 liters into milliliters. So the first thing we're going to do, we're going to write down the only number that's present in this question. So that's 1,895. And we're going to put our units. Because if we have our units, then we can trace along what numbers we need to put in. So this is 1,895 liters, and we're going to put a placeholder on the bottom. So now we're going to have to multiply. And if we look, we want our answer to be in units of milliliters. That's what it asks for. So if I want units of milliliters needs to be right here. In order to convert this, I have to cancel out units of liters. So liters needs to go on bottom. So 1 liter has 1,000 milliliters. Milli is 1,000 times smaller. Kilo is 1,000 times bigger. So if we look now, liters cancels with liters. The only unit I'm left with is milliliters, which is what I want my answer to be in. So now I just got to go ahead and do my math. If I do 1,895 times 1,000, I'm going to get 1,895,000. And because I'm multiplying by 1,000, all I had to do was add 3 zeros onto the end. Number 2 is a question about significant figures. Now the math to this is pretty easy. What we're going to have to do, we have the starting volume of water and the final volume of water after we've added a metal cube. So a student is trying to determine the volume of a metal cube. He decides to fill a beaker up with 500 milliliters and drop the block in. He will use the displacement of water to determine the volume of the metal cube. His results are below. What is the volume of the metal cube with the correct number of significant figures? So that's the key statement there, the correct number of significant figures. So in order to solve this, we're going to have to take 500 and subtract it from 560. So if we do 560 minus 500, we're left with 60.3. Now, if you look here, this guy's got 1 decimal place, whereas this guy has 2 decimal places. Our answer can only be as accurate as the least accurate measurement. So this is the least accurate measurement, and it has 1 decimal place, so my answer can only have 1 decimal place. If you put down 60.30, that would be wrong. It's got to be 60.3. It has to have the same number of decimal places as the piece of data with the least number of decimal places. The last one is asking to give us an example of a substance that can be chemically decomposed. Anything made of 2 or more elements can be chemically decomposed. If it's a pure element, you chemically cannot decompose it. So the trick here, anything that's up on the periodic table by itself is not going to be decomposed. Anything that's made of 2 or more elements can be. So a good example could be magnesium chloride or sodium chloride. Pretty much anything that's got 2 elements in it is going to work. Now in the case of O2, okay, this does have 2 or more elements, but they're both oxygen. So this isn't going to break down into anything else. It's still going to be oxygen. So part 4 are the BCRs. And there's 2 BCRs. The first BCR asks us to compare Thomson and Rutherford's model. And if you read the question, there's a lot of information in the question. It tells you what Thomson's model was called, what it looked like, and it tells you that Rutherford did an experiment where he shot positively charged alpha particles at a thin piece of gold foil. So the first question asks us, considering the structure of the atom, why did most of the particles go straight through the foil? Well, that's because the atoms are mostly empty space. So here's the path of the alpha particles, and whenever they fly through the atoms, they don't encounter anything, so they fly straight through. The second question asks why a few of the alpha particles were deflected. So some of the alpha particles were deflected because they hit dense, positively charged nucleus. So here we have our nucleuses, we have our atoms, and here's the path of the alpha particles. So occasionally an alpha particle comes in, and as soon as it hits the nucleus, it bounces off. So as that alpha particle comes in and collides with the nucleus, it bounces off. And that's because they're hitting something that's very dense and very heavy. It's kind of like you threw a marble at a bowling ball. If you throw a marble at a bowling ball, the marble is going to bounce back. So the last part asks you to explain what changes would be made to Thomson's model based on Rutherford's experiment. So the first thing you would do is add a nucleus. This is why some of the alpha particles bounce back. And if you notice here, I don't just say add a nucleus. I say add a nucleus and I explain why. In order to get a 4 out of 4 on your BCRs, you have to back up your claims with evidence from the experiment. In addition, that nucleus must be positive in order to hold on to the negative electrons, and it must be positive in order to deflect the positive alpha particle. The rest of the atom is empty space in which electrons orbit the nucleus. So this is why most of the alpha particles go straight through. And here we have a picture of Thomson's plum pudding model. You've got a sphere of positive charge, that's like the pudding, and then you have negatively charged particles. Those electrons act as the plums. In the Rutherford model, we have our dense, positively charged nucleus with a lot of empty space in which the electrons move through. BCR2 is asking us to design a procedure to determine if an unknown sample is a metal or a non-metal. So this is what we did in class with our lab. What I recommend you do, the first part of the question asks for materials. I would skip that for now and go ahead and write your procedure, and then go through your procedure and underline the things that you need and then write them down as the materials. So we're going to skip materials for now. We're going to go to the procedure. So the first step that you're always going to do is to gather your materials and put on your goggles and safety equipment. The next step is going to be to observe the unknown. We're going to record its color, luster, and state of matter. Next, we're going to test the unknown for malleability by hitting it with a hammer. If it bends and is flattened into a sheet, it is a metal. If it shatters, it's a nonmetal. So an example of a nonmetal would be the sulfur that we had, that yellow solid material. Whenever you hit it with a hammer, it shattered into fine powder. Then we're going to use a conductivity tester. That was the battery with the probes. We're going to place the probes onto the sample. If the tester lights up, the unknown is a good conductor and it's likely going to be a metal. If it does not light up, the unknown does not conduct and is a nonmetal. The last test we're going to do is to drop a small piece of the unknown into a beaker of hydrochloric acid. If a strong reaction is noted, then the unknown is a metal. If nothing happens, then the unknown is a nonmetal. Then you're going to have to record your observations, and so we don't leave a mess, we clean up. So now that we've written our procedure, we can go through and highlight the things that we need. So we're obviously going to need our goggles. We're going to need our safety equipment. So that's closed-toed shoes, gloves, any of that kind of stuff. For the next step, we're observing the unknown and recording its color, luster, and state of matter. Well, we don't need anything for that. We just need our eyes. The next part asks us to test for malleability by hitting the unknown with a hammer. So I'm going to need a hammer. Next step, we use a conductivity tester to test the unknown. We're also going to need to drop a piece of the unknown into a beaker of HCl, so I'm going to need that. Now the only other thing that I need is going to be the unknown itself, so I'm going to need some unknown to test. So if we go back to our Materials, there they are. We need the hammer, the conductivity tester, hydrochloric acid in a beaker. We need an unknown sample to test, and we need our safety equipment. So the next thing that we got to do for this PCR is to show a sample data table. So here's one that I made. Now, based on the evidence in this data table, I would conclude that my unknown was a metal. So the first test was the hammer whenever I was testing for malleability, and it flattened into a sheet without breaking or shattering. The next one is conductance. It was a good conductor, which means that the conductivity meter was brightly lit. The next one was reaction with HCl. It bubbles and fizzes and heats up during the reaction. For appearance, I have a metallic gray shiny solid. So that's the kind of data that you would collect, and this is a sample data table. The next one asks you to explain what your findings mean. So here we have the same table from the previous question, except now I've added on another column for meaning. So if it flattens into a sheet without breaking or shattering, it is malleable, which means it's a metal. If the conductivity meter is brightly lit, that means it conducts well, which makes it a metal. If a reaction occurs, we see bubbles and fizzing, then it's a metal. And for the appearance, it's metallic, gray, shiny, and it's a solid. So it looks like a metal. So based on this evidence, I would conclude that my unknown sample is a metal.